Okay, so thank you for the introduction, and thank you to the organizers for the opportunity to give a talk here. So I'm going to be talking about a very classical problem concerning Hermitian L1 algebras, but I'm going to be talking about an entirely new approach to this problem. So a bit of background. I'm working operator algebras and non-commutative geometry. No knowledge of either of these fields will be assumed, but that also means I'm going to be slightly vague in the full statements of the main theorem, as to not just overload you with some extra details, which is really of no matter and shouldn't be the main takeaway from this talk. What I'll do is I'll get everyone on the same page talking about what Wiener's lemma is. I assume everyone here has seen this before, but let's agree on what Wiener's lemma is. I'll then give you a reformulation of Wiener's lemma in terms of convolution algebras. I'll then show you how we can use derivations, specifically derivations of the bounded operators on L2, to recover Wiener's lemma, or a stronger version of this, and I'll apply it in the case of discrete groups, and I'll indicate how you can recover the locally compact case at the very end. The reason I have not included this is it gets very, very technical. See now that I have not started a watch. Okay, so Wiener's lemma says that if I let W be the space of continuous functions on the circle, which I'll denote by T, for which I have a summable Fourier series, then if F is in W and F is nowhere zero on the circle, so it has a pointwise inverse, if you view it as an element of C of T, then its inverse, 1 over F, is also going to be such that it has a summable Fourier series. And what I'll do, I'll use the duality between the circle and the integers, and the Fourier transform, and reformulate this in terms of properties of convolution algebras. So, in this talk, gamma will denote a countable discrete group, and from a countable discrete group, I can make its group algebra, which I'll denote by CC of gamma. Formally, it's just a C-linear span of the sort of the canonical generators delta x. This becomes a star algebra if I put on it multiplication, which is convolution, so f star g of x is given by this sum that you have all seen before. And technically, there's also an involution, which plays a very important role, but not in this talk. But, well, it's given by f star in x. It's given by the complex conjugation of f evaluated in x inverse. This should hold for all f and g in CC of gamma. Now, CC of gamma is going to be too small for our purposes. It's rarely going to be Hermitian. So I'm going to be interested in some completions of CC of gamma. I, of course, have the 1 norm, so I can complete CC of gamma in the 1 norm, and I get the algebra L1 of gamma. This is a Banach star algebra, where the operations are just given by the extensions of the convolution and the involution formula written above. And this is the main object of interest. We want to study Hermitianness of this thing. Now, we want to study, Hermitianness is going to boil down to spectral invariance of L1 inside a C-star algebra. Specifically, one obtained through the left regular representation. So I have the left regular representation of a group. I integrate this to the left regular representation, which is a star representation of CC of gamma. This is just viewing CC of gamma as bounded operators on L2 through left convolution. So lambda of f acting on an L2 vector now psi is given by the convolution of f and psi. We've also probably all seen this before. Now, what you can do then is you get a closure in the operator norm. So I close off either CC or L1, doesn't matter, in the induced norm, and I get the reduced C-star algebra of gamma, which I'll denote by C star R of gamma. If you're not very comfortable with C-star algebras, think of this as B of L2. Okay? So feel free to think of everything as happening on the C-star algebra, B of L2 of gamma. So then I can reformulate Wiener's lemma in the following way. It is really just a statement that L1 of the integers is spectrally invariant in C of t, which through the Fourier transform, I identify with the reduced C-star algebra of the integers. Now, this is also equal to the full C-star algebra of the integers, if you're familiar with the full C-star algebra. Spectrally invariant will mean that for every f in L1, the spectrum of f viewed as an element in L1 is the same as the spectrum of f viewed as an element in the C-star algebra. This really just, this is what Wiener's lemma is. But unlike Wiener's lemma stated on the first slide, this question makes a lot of sense in a more general context. So I can ask the question for what potentially locally compact, but we'll stick to discrete for the sake of exposition, for what potentially locally compact groups is it true that I have this spectral invariance condition? And if I have this spectral invariance condition, I will say that G is Hermitian. Now, I'm slightly lying here because on the right-hand side, I really want to say that the spectrum in L1 is the same as the spectrum in the full C-star algebra. This is automatic for any group that is known to be Hermitian because Hermitian groups are amenable, but that is slightly besides the point. Now, there are some known cases for where this is true. So, by result of Victor Losot from 2001, this is true whenever my group is compactly generated or finitely generated in the discrete case, a locally compact group, and I have polynomial growth. I'll get to what polynomial growth means later, but for the people who know already, this is sort of the, I would say, still very much state of the art. Those are not all the groups we know it for, however. We also know it, for example, for the AX plus B group and some individual other examples, but they're studied more on a case-by-case basis rather than just by providing an entire class for which you know this property. Now, let me comment on two things when it comes to Losot's result. First of all, you can absolutely not remove compact generation. Okay, so if you remove compact generation, you can indeed find discrete counterexamples. You can find locally finite counterexamples. So there are infinitely generated groups for which every finitely generated subgroup is a finite group for which this fails, which are not Hermitian. So you cannot remove compact generation. The second thing is, coming from non-commutative geometry and operator algebras, I'm interested in this not necessarily for groups, but generalizing this to other areas of mathematics where L1 algebras make an appearance. Now, I'm not going to be talking about either of them, but recently, L1 of groupoids and of discrete quantum groups have seen some interest. So establishing a Wiener lemma in these situations is desirable. Now, the proof for groups of polynomial growth really hinges on understanding that these groups have a certain structure. You understand a lot of the structure of these groups. I will not make the same claim in the other cases I mentioned, groupoids and quantum groups. I don't want to carry that proof over to those settings. So the question I set out to answer today is, can we find a way to reprove Losot's result without needing to use the structure of compactly generated locally compact groups of polynomial growth? And I'll tell you exactly how to do that. And it goes through derivations on C-star algebras. Again, feel free to pretend that everything is B of L2. But I need to talk about closable star derivations or closed star derivations on C-star algebras. So if B is a C-star algebra, then a closed star derivation is going to be a linear map on some star subalgebra of B, which takes values in B. So it's from B to B, but it's potentially only densely defined, or just not defined on all of B, for which I have the Leibniz rule, which is the first condition here, saying that I interact nicely with products. I should also, I've said star derivation, so my derivation should also respect the involution. So in particular, delta of B star should be the involution of delta of B. And lastly, to do any sort of meaningful analysis, all of which I'll sweep under the rug because it becomes very non-commutative geometry heavy, but I need the domain, I need delta to be a closed map with the specified domain. It will not be enough for us to look at derivations. I will need to start iterating these derivations. So by dom delta n, I'll mean the domain of the n times iterated derivation. Now, just so we're all on the same page, if I were to, for example, require that delta is densely defined, there is no guarantee that delta squared, delta cubed, etc. is densely defined. It's going to be the case for L1 algebras and derivation I'll show you, but this is not true in general. And indeed, we might even need the smooth vectors. So by dom delta infinity, I will mean the intersection of all of these dom delta n's. These are the smooth vectors for delta. And I'll tell you then this main theorem, which I'll show you basically the sketch, only the parts that are truly the takeaway, and I'll hide some of the extra details that are actually truly necessary to be there, but they just sort of clutter the exposition. If I have curly A Banach star algebra, this is going to play the role, or L1 is going to stand in for this curly A later. If I have a Banach star algebra, which densely embeds into some C-star algebra, capital A, and I have some delta, which is a closed star derivation on some super C-star algebra, by which I mean a possibly larger C-star algebra, which A sits inside. For example, B of L2. If there is some n, either a natural number or potentially infinity, for which I have dense embeddings of the intersection of the C-star algebra A with the domain of delta n into my Banach star algebra A, and then into the C-star algebra A, which I'm assuming that I have, then I can always guarantee that this curly A is Hermitian. And in the sequel, this capital A, the role of this will be played by the reduced C-star algebra. As I mentioned, this curly A is going to be L1, and thus, in light of the main theorem here, or the sketch of the main theorem, what I need to do is find a suitable derivation delta on some suitable C-star algebra for which I can guarantee that I can sandwich my L1 algebra in between the reduced C-star algebra, which is fine, and the intersection that's always fine. They always have that embedding, and the reduced C-star algebra intersected with Dom delta n. Okay, so I can do this under certain assumptions. So I need to start talking about length functions. I've already kind of talked about length functions because I've mentioned groups with polynomial growth, right? So you have polynomial growth with respect to a length function. I'll now tell everyone in the audience what this actually means in the case of discrete groups. So by a length function, I will, on a discrete group here, I will mean a map from gamma into 0 infinity, for which, well, I need to send the unit in the group to 0. Okay, that's a requirement. I want to respect inverses. This has to do with the star algebra properties. I want to respect inverses in the sense that x and x inverse are sent to the same number for every x. I also want to interact nicely with products. So I'm going to require that L of xy is bounded by L of x plus L of y for all x and y in gamma. Now, when I say length function, even if I should forget it, what I will actually mean is a proper length function. I'll tell you why this is necessary in a second, but L is proper if it is a proper map. In particular, if every finite interval 0 to r, for every r, I take the preimage of this under L, I get a finite set. The reason why I need this has to do with, well, let's look at sort of the canonical way of constructing a length function on a discrete group, which is generated by some symmetric generating set. Symmetric here means that if x is in S, so is x inverse, right? So I have such a set S. I will define the word length function associated with S as the following. I'll just say ls of x is the minimum number n, such that I can write x as a product of S1 through Sn, where every Si is in S. And then ls is a length function, which you can easily verify, and it is proper if and only if S is finite. So the reason I need properness is, well, I mentioned earlier that this compact generation absolutely cannot be removed. So the fact that I cannot remove compact generation in the statement about L1 algebras is reflected in the fact that I can only handle proper length functions. This is, for example, fine if whenever I have a finitely generated group of polynomial growth, this is going to be fine. So let me tell you what polynomial growth is. I'll say that a pair consisting of a group gamma and a length function L has polynomial growth if there exists some numbers C and K such that I can bound the cardinality of the L balls polynomially. So I can bound that specifically the cardinality of the L ball of radius t is bounded by C times 1 plus t to the power of k for all t larger or equal to 0. And I mean, the L ball of radius t is exactly what you think it is. It's exactly the element x that has length at most t. And just as a piece of information for maybe not everyone is familiar with this, if I have a finitely generated group of polynomial growth with respect to some length function coming from a symmetric generating set, this is exactly a virtually nilpotent group. This is Gromov's theorem on polynomial growth. Okay, but we are in search of a derivation, and we want to squeeze our L1 algebra in between two algebras. One is fine. The other comes from the derivation that I now have to construct. So this leads to from a length function, I can then construct a Dirac operator on L2, and I don't really care about what the full domain of this thing is. what I'll do is I'll specify what it does on the canonical generators, right? So for now, this DL is a map from CC of gamma. I view CC of gamma as sitting inside L2 of gamma. And what I'll do to my canonical basis is I'll just take delta x and I'll rescale it by L of x. And then I take the closure of this and I'll denote the closure by exactly the same symbol. So that's also going to be DL. What this does is it allows me to construct a closed star derivation where I'm going to be a bit vague about what the exact domain delta here is, but it takes values in B of L2. And what I'll do is I'll take F in CC of gamma, which is really the only thing we're going to care about. I'll take F, I'll send it to lambda of F, which was the left regular representation. I'll then take the commutator with DL, and what I get is an operator which is not necessarily everywhere defined, but it is extendable to a bounded operator. So I take the closure of this, and for the purposes of having a star derivation, this is really of no matter. But let's just be consistent. I'm also going to multiply by I, the imaginary unit. If you don't do this, you get an anti-star derivation, and your life's still fine. But let's just be consistent with the earlier slides. And in particular, what I want you to make note of is, well, if I take the commutator of DL with lambda of F, what I actually end up with, if you sit down and do some calculations, you end up in an algebra that's generated by the left regular representation and also pointwise multiplication with things coming from L infinity. But L infinity acting by pointwise multiplication, you will see that, well, these things actually commute with DL. So when I start iterating the derivations, things coming from L infinity doesn't matter. So what I care about is only things that come from CC of gamma. And in particular, if I keep just having F inside CC of gamma, I can start iterating this. And I will always have that CC of gamma, viewed now as a subspace of B of L2, is in the domain of the n times iterated derivation. In particular, will then sit inside dom delta infinity. Yeah, so I have CC of gamma is inside dom delta infinity, potentially, intersected with the reduced C-star algebra. So what we can do then is we can recover the result of Austad in the case of polynomial growth. So straightforward calculations, which I'll also hide, but they are truly straightforward. They're well known in the theory of rapid decay groups, will show you that, well, I can look at the smooth vectors, dom delta infinity. I intersected with the reduced C-star algebra, so now I'm looking at the smooth vectors for delta that are also in the reduced C-star algebra. This will exactly coincide with this set, which is in the middle. The set of all F, here I've forgotten to write that it's all F in the reduced C-star algebra, for which this Sobolev norm is finite for all S larger or equal to 0. So these things are really things that come from the theory of rapid decay groups. And this set here in the middle, I'll denote by H infinity L of gamma. This is consistent with Sobolev norm, with the terminology or notation used in the theory of rapid decay groups, studying these Sobolev algebras. And it actually turns out that, well, okay, now I have this H infinity, but this thing you can sit down and just do a very, very basic one norm estimate using Cauchy-Schwarz. And what you show is that if I have polynomial growth, then H infinity will embed into L1 of gamma. In fact, the existence of this embedding is equivalent to gamma having polynomial growth. So I can really only do this if I have polynomial growth. But in light of what I showed you earlier, I have now managed, if H infinity is this intersection of dom delta infinity with the reduced C-star algebra, what I've then done is I have sandwiched my L1 algebra in between the reduced C-star algebra and the intersection of the reduced C-star algebra with the smooth vectors for a derivation. And the main theorem will then tell you that if I have a pair gamma L, which has polynomial growth, then L1 of gamma is Hermitian. Now, that only recovers the discrete part of Austad's theorem. And I want to now indicate what you can do, but I don't want to write anything because it gets incredibly technical, but what you can do to actually recover the compactly generated, locally compact version of this. So the issue lies in that the equality at the very top here, this dom delta infinity intersected with the reduced C-star algebra being equal to the middle sum, is no longer true on the nose. And the issue for the people in the audience that are familiar with C-star algebras, with group C-star algebras, is the fact that if I'm a locally compact group, then my reduced or full C-star algebra does not embed into L2 of the group. This poses quite a big technical obstacle. It can be circumvented. Indeed, it was done so by Xi and Schweitzer back in 1993 in a paper on rapid decay for cross products over locally compact groups. It's a very technical paper. It's hard to see what's actually going on when we translate it to our setting. But if you're willing to believe me that the top equality there can be tweaked a little bit by taking the intersection with an additional ideal in the so-called row algebra of G, then what we have done, and again, taking intersections with C-star algebras is not going to affect hermitianness, we recover Lostad's result. So if I have a compactly generated, locally compact group of polynomial growth, then L1 of G is going to be a Hermitian Banach star algebra. So that recovers the theorem, but I don't really want that to be the main takeaway, because my motivation for doing this is not to reprove something which is already known. As I said, my interest in this is really more in that I can do this for other Banach star algebras, specifically L1 algebras appearing elsewhere in mathematics. But you might also have a favorite Banach star algebra, and you might worry, is my Banach star algebra Hermitian? Do I have spectral invariance of this Banach star algebra inside my enveloping C-star algebra? And what I want the main takeaway to be is really what I wrote on the main theorem, which is that we can, using non-commutative geometry, but hopefully I can present this theorem in a paper in a way that you don't really have to care about the details, but I can generate Hermitian Banach star algebras by showing that I can sandwich them in between its enveloping C-star algebra, which is always fine, and taking the enveloping C-star algebra and intersecting that with the domain of, with the DOM delta infinity for some delta existing on A. So that's all I wanted to say, so thanks.